Hello, everyone. I'm Anupam Datta. Today, I'm going to be part of a team that presents this tutorial from explainability to model quality and back again. Along with me presenting will be Matt Fredrickson and Klaus Leno from Carnegie Mellon University, as well as Shayak Sen, who along with me is a co-founder of Truera, and we were both also at Carnegie Mellon. And two other co-authors who are present here to answer questions and participate are Kaiji Liu and Zifan Wang, who are both PhD students at Carnegie Mellon. The tutorial will be divided into three sections. We will start from explainability, and in particular highlight axiomatic foundations that can provide a systematic way of understanding explainability. From there on, we will go on to a second section where we will look at how explainability can be a means to improve the quality of machine learning models along various dimensions, in particular privacy and fairness. And in the third and final section of the tutorial, we'll come back from model quality to explainability, in particular examining robustness of machine learning models and how that can in turn inform desiderata for explainability of models. To get started, and this is well-known context for this audience, machine learning systems are increasingly becoming ubiquitous. They are no longer confined to the big tech companies, the Googles and Microsofts, Amazons and Facebooks of the world, but are increasingly finding their way into high-stakes use cases, like in finances, in financial services, credit decisioning, healthcare, education, as well as in the public sector and government spaces. And while that brings a lot of promise into high-stakes areas, it also raises questions of trust and model quality. As we start adopting more complex machine learning systems, many of these systems remain quite opaque. Consider this credit classifier that processes Joe's loan application and decides to deny him credit. At that point, an immediate question is, why was Joe denied credit by this tree ensemble model? Historically, these kinds of decisions have been made by more simpler linear rule-based systems or linear models that are fairly easy to explain. But once you get to tree ensemble models with hundreds or even thousands of trees, the question remains non-trivial to answer. If you want to take an example from healthcare, this is an example where a deep neural network, let's say the Google Inception Net, is processing medical images of the eye in this case, and it comes up with a prediction that this image indicates that the individual, the patient, suffers from a severe form of diabetic retinopathy. It raises a very similar question. Why did the model come up with this diagnosis? And this kind of explanations serve as a way to enhance transparency in machine learning models and to build trust in them. But perhaps even more importantly, they can serve as a foundation to assess and improve the quality of machine learning models. In this tutorial, and the position that we have taken based on over 6-7 years of research now in this area at Carnegie Mellon, starts from some fundamental questions. The first one is, what are requirements for good explanations? And that's one of the questions we'll look at in some detail in this tutorial. And then moving on from there to a more consequentialist question of how can explanations enable the assessment and improvement of model quality. And by model quality here, we refer not just to accuracy of models, but other dimensions are such as privacy and fairness and robustness of models. And these are some of the key questions that we will examine in this tutorial, providing an overview of a set of key results, a big chunk of which has emerged in the community over the last few years. It will include several results from our team, but also place that in the context of other results in the neighborhood from folks in universities and research labs working on these topics. And some of the motivations here will emerge, motivating applications we'll turn to are in finance, from finance and healthcare, but the methods are very broadly applicable and cut across a whole host of other verticals as well. Let's first turn to this question of explanations and machine learning model quality. A lot of the practice of machine learning has historically focused on model accuracy metrics such as AUCs and Gini, F1 scores, and metrics like that in assessing the quality of machine learning models. Part of our thesis and position is that there's a lot more to model quality than simply accuracy. There are questions around robustness of models, privacy, fairness, as well as a set of other elements that help with improving the accuracy of models as well by addressing problems with data bias, with reliability or certainty in model predictions, and elements of conceptual soundness, which ties back to causal relationships that a model may or may not have learned. And that's the space in which there's both a set of work that is starting to emerge, as well as practical demonstrations showing that we may want to focus research attention on this connection between explanations and assessing and improving the quality of machine learning models. A second element of explanations is that it can be a basis to enhance trust and transparency in machine learning models. We have seen that in the context of banking and insurance, healthcare, and a number of other verticals as well. And that requires a foundational understanding and set of requirements around which we may want to converge as the field starts getting more mature in laying out foundations for machine learning explanations. Let's transition into the foundations of explainable AI. We started off with this example of an individual who was denied credit, leading to the question of how would you explain this denial? Before we get into specific mechanisms, let's spend a few minutes just thinking through what requirements for good explanations might look like. There are several dimensions to these requirements. One is that it should be able to answer a rich set of queries about the model's behavior, explaining individual predictions, as well as more aggregate trends that a model might exhibit. And in a minute, I'll give you some examples of what kind of queries are often commonplace. A second item here is that explanations should capture causal influence. It's very common for inputs that are fed to a machine learning model to be correlated, in some cases even strongly correlated with each other. Being able to tease apart which of several different input features actually cause the model's predictions is very powerful for a number of different reasons. It helps to understand the model in a way that you can act on it in a way that you can address problems of privacy, you can address problems of fairness, as well as do root cause analysis in a way that might help with improving the accuracy of machine learning models as well. The third requirement is that the explanations should reflect the power of a feature. And I'll bookmark this and get into it in a couple of minutes, elaborating on what I mean by power. And finally, explanations have to be accurate in a specific way, which is also something that I'll elaborate in a few minutes. So let's focus on one kind of explanation method, which generates input feature importances. So Jane here was denied credit, and this explanation is telling her that of all the features that went into the model, her annual income, the term duration, and installment of the loan were the most important features that led to her denial. And moreover, there's a quantitative presentation of how much each of these features contributes to the model's overall assessment of risk. On this side are the features that, like home ownership status, debt to income ratio, and loan amount, which reduces the risk assessment coming out of the model. Input feature importances have been around for a while now and are increasingly starting to get used in high stakes use cases in finance, healthcare, and a number of other marketing and a number of other use cases as well. What I would like to do is highlight a few of the important pieces of work in this area and then provide a high-level overview of where the common denominator is and how various methods stack up against the requirements that I outlined a couple of slides ago. An important piece of work here is that on permutation importance from Bryman back in 2001. It was originally designed to not to provide a means to explain model predictions, but rather to help with feature selection. But it has been adapted to explain and compute input feature importances in various settings. In 2016, out of CMU, we wrote a paper called Quantitative Input Influence, along with Shaik Sen, who's a co-author on this tutorial, and Yair Zik, now a professor at University of Massachusetts. This work was one of the first ones that introduced the use of Shapley values and ideas from causality to compute input feature importances. Around the same time, a month or two later, a paper called Line came out of the University of Washington. And then later in 2017, there was a paper on Shapley additive explanations also from folks at the University of Washington that also provides a way to compute input feature importances. Later in that year, integrated gradients came out of Google, Sundarajan et al. And in 2018, some of us on this tutorial, Klaus Leno will speak later in the session, Shaik Sen, I and Matt Fredrickson, along with Linyi Li, wrote this paper on influence-directed explanations for deep neural networks. So these are some of the pieces of work that we will touch on in this tutorial. It's not meant to be an exhaustive list, but it is. There is a common denominator here in terms of axiomatic foundations that we will get into in a little bit. Let me start by highlighting some of the similarities across these methods. The first step is to define what queries or what questions about the model we are trying to answer. We can answer questions such as, why does the model have a score of 665 for Jane? Or why does it have disparate impact? Or why did the model deny Jane? So specific questions involving individual predictions as well as aggregate model behavior. Once we have defined what question we are trying to answer, then there is a form of causal testing. On one side here is Jane, who got a score of 665. And then we go on to create a bunch of near clones of Jane who differ from Jane in carefully controlled ways in one or more features. We run these clones through the model and observe how the model is treating these individuals, or in other words, how the model outputs vary. If the model outputs vary a lot when a feature is changed, then that feature is likely important. If the model output does not change too much when a feature or a subset of features are changed, then that feature or subset of features at a high level is not that important for the model's predictions. There is a fair bit of nuance here. If you were to vary just one feature at a time, then that would get you closer to what permutation importance does. That works fine for linear models, but as you go to models with nonlinear interactions, that method would miss out on interesting feature interactions. So you may have to vary subset of features at a time, but that, on the other hand, raises some challenges with scalability, which have to be addressed carefully. So if you have a model which takes as input, say, 100 features, and you have to consider all possible subsets to account for feature interactions, then you start getting into a realm of a very large computation in this causal testing process. Finally, in the summarization step, we take all of these intermediate results that on how the model treats these near clones and summarize them in a way that you can get these feature importance scores, where you may get an answer of the form that of the 665 score for Jane, her score went up by 133 because of her low debt-to-income ratio, and the score went down by 45 because of her income, and so forth. This summarization step can also be done in many ways. Some of the methods I highlighted on the previous slide have started converging on the use of axiomatically justified summarization methods, such as Shapley values and Hammond-Shapley values, which have some nice properties that I'll get to in a little bit. With that overview, let me dig into a few high-level concepts here which are worthwhile to focus on. The first is this notion of a power of a feature. And a good way to think about it is think of the US presidential election and how much power a state has in determining the election results. Now, it depends quite a bit on what query you are trying to answer. If you're trying to answer the question of which states contribute the most electoral college votes, then the answer to that would be states like California and Texas, which bring in the largest number of votes. If, on the other hand, you're focusing on a different question, which is like a classification question, which states decide the winner, then states like Pennsylvania end up being a lot more influential. The causal influence of Pennsylvania, the swing states, end up being a lot more important. This is an important analogy to keep in mind because just the US presidential election is like a linear classifier. And for that election, the feature that, depending on whether you're trying to explain the regression score, which is the total number of electoral college votes, or the classification outcome, which explains who won the election and for what reason, the answers can be dramatically different. And this does carry over in a very systematic way to more complex machine learning models, where the analog of the regression score is like the risk score or log odds score coming out of a tree ensemble model, and the analog of this particular classification outcome is the result of a nonlinear transformation on the risk score. And the top features could be dramatically different based on which question or which query you're trying to answer or explain. Power depends on marginal influence. So one way to think about this is, if you think about what is the effect of Pennsylvania after the results from Indiana, Georgia, and Maryland are in, at the point when these three states had declared the results in the 2016 presidential election in the US, the forecast was 67% in favor of Clinton. And then Pennsylvania came in. It was won by Trump. And there was a big swing at that point. And the forecast at that point went from 67% for Clinton to 54% for Trump, which is about a 20% swing. And that 20% was the marginal influence of Pennsylvania in this election. Now, for a classification outcome, the order in which the results come are not very important. And so the way in which you go from marginal influence of a specific feature to a specific set to getting to a single number that measures the marginal influence of that feature or state in our example on average is by averaging it in some form. And one way to do that averaging is to use the Shapley value. The details of exactly what the Shapley value is computing here is not perhaps that important. The high-level point to note is that it's one specific way of averaging marginal influence. And what's nice about it is that it's axiomatically justified. There are some very natural axioms that the Shapley value is the unique value that would satisfy these axioms. At a high level, these axioms, symmetry, dummy, and monotonicity, capture some very natural properties. Symmetry is saying that equal marginal contribution implies equal influence. If you have two cloned features, for example, age and say date of birth, and they have equal weight in a linear model, as a concrete example, then they would have equal influence. Dummy is saying that if a feature is never touched by an ML model that consistently has zero marginal contribution, then that should have zero influence. And monotonicity is saying that if a feature has consistently higher marginal contribution for me than it does for Matt or Shayak, then the overall feature influence of that feature for me will be higher than that for Matt or Shayak. That lets us compare across individuals, which is extremely powerful, not just for explaining individual predictions, but also for some of the model quality assessment related to stability and fairness of models. Now, one of the key challenges here is that efficient Shapley value estimation is hard because the exact computation is exponential in the number of features. However, there are different methods that people have come up with, including some of our own work on efficient estimation through sampling and leveraging structure of tree models that can get performance down to milliseconds and even lower through distributed implementations. Another nice thing about our results is that they come with pack-style bounds on accuracy of estimation. So you can have a high degree of confidence that the estimation is close to the true value. And in various empirical experiments that we have done with actual data sets for production models, as well as public data sets on which we have built our own models, there's very high empirical accuracy of the estimation method. Some takeaways from this section is that Shapley value-based methods can be the basis for meaningful reason codes, the kind of reason codes that are required, say, under the equal credit operator. The reason codes may vary significantly based on which comparison group is chosen, meaning that if you're trying to answer a question like, why was Jane denied credit relative to the set of people who are approved, versus why was Jane denied credit relative to all the people who applied, the answers of which features are the most important can vary dramatically. So it's important to be specific about which comparison group you're using in generating the clones in step 2 of the method. Explanations also vary a lot based on model output type. So if you're trying to explain log odds using, say, an open source library like TreeShap, versus you're trying to explain classification outcomes, which is the kind of thing that's required when you're trying to generate reason codes, let's say under EQUA, the most important features might vary dramatically. Explanation accuracy is also critical. The estimation needs to be accurate for risk scores, probabilities, and classification outcomes. Let me transition now to explaining deep neural networks, and I'll provide a few examples here to illustrate the concepts. As we start getting into deep neural networks, we will start with input feature importance, but we will also start transitioning into internal explanations, because a lot of the interesting action in deep neural networks happens in the deeper layers of the network, where higher level concepts are learned, and explanations can start getting more detailed if we start peering inside of these networks. Our starting point from our conversation is the integrated gradient method by Sundarajan et al. At Google. It's a natural neighbor to the Shapley value work that we just presented. As you move from discrete features to more continuous features like those that appear in images, there is an adjacent concept of Almond-Shapley values, which was adapted to the setting of neural networks, which are continuous differentiable functions operating over, let's say, images as one kind of concrete example. The integrated gradient here does a form of average marginal influence, where at a high level, what the method does is that it computes the gradients along a linear path, starting from a baseline point, which could be the all black image, to the image that is to be explained. In this example, this X over here. And it'll compute a bunch of gradients along this path and then average them to compute and multiply it by the difference between X and XB to get a contribution of the different features to the model's prediction. This idea is a natural adaptation of the use of Shapley values to this context, and there has been a lot of follow-up work building on it in the literature. The integrated gradient also has an axiomatic foundation, very similar to that of traditional Shapley values, with some adaptations for the setting of differentiable continuous differentiable functions. And these are some examples of what an explanation of this form might look like. Here's the original image, a camera, and you can see in the integrated gradients view what part of the image the model focused on in order to conclude that this is an image of a camera. And over here is a fireboat. Similarly, you can see that the explanation has picked up on the distinctive characteristics of the fireboat, which is putting out these streams of water. What I want to go into next is some of our work on this topic on inference-directed explanations, where we wanted to go a bit deeper into the network. Going beyond input attributions, we wanted to get into internal attributions. We are interested in internal representations because we wanted to see what higher level concepts the network has learned that lets it figure out, for example, that this is an image of a sports car. And in that process surface, what each neuron or each important neuron learns that leads the model to this prediction. So what is the key concept related to the label over a distribution of inputs? And what concept does each neuron learn? Those are the kinds of questions that we would like to answer with this method. Here are some examples of what an explanation, an inference-directed explanation might look like. Here's Orlando Bloom, and his face was correctly classified as Orlando Bloom's fame by a deep neural network, a VGG16 network in this case. And then when we applied our tool for influence-directed explanations to that network and looked into an intermediate layer of the network, the higher level concepts that the network had focused on to arrive at this prediction were his left eyes. These are the three most important neurons and what they're focusing on. Two of those neurons are focusing on his left eye, and the third neuron is focusing on his lips. So that's what makes Orlando Bloom from the standpoint of this VGG16 network. Here's another example. This image was identified to indicate diabetic retinopathy stage 5, an advanced form of the disease. And while applying the influence-directed explanation tool to it, it surfaced that the most important feature that internally was learned, which led the model to this prediction, was focusing on this region in the image where the lesions are. And the most important neuron, which was pushing the model to believe that this is a normal eye, not afflicted with diabetic retinopathy, was focusing on the optic disc area, part of the eye where there weren't any indications of diabetic retinopathy. So what this kind of explanation brings beyond input level explanations is understanding of what are the most important internal network units, and moreover, what concepts have they learned? What parts of the image in this case are they focusing on? And at a high level, we would like these explanations, the requirements for good explanations in this case, to be causal, succinct, and importantly also be distributionally faithful, meaning that the model should be fed familiar inputs to those that it saw during training. And the way that these explanations are going to be generated, a key piece of it is a measure of distributional influence, which works with a slice of the network. An intermediate layer is one way to think about it. And within it are units. The units could be neurons or they could be channels. And once we focus on that unit, we'll associate with it a feature importance score, much like we did before for input features. And the way in which this feature importance score is computed is through this process here. The details of it are perhaps not important, but let me highlight a few things that are of note. First is that the distributional influence is an average gradient. It's an average gradient over a distribution of interest. And it's computed by focusing on a slice of the network. In this case, we are focusing on a specific neuron, ZJ, in this slice. We compute the gradient of the quantity of interest, some function of the output, GZ, with respect to this neuron, ZJ. So the higher this gradient, the more important is this neuron or network unit in impacting that quantity of interest, that model output characteristic that we care about. The next thing to note is that the gradient is with respect to the network unit, and it's weighted by a probability of the input x from some distribution of interest. So having flexibility in the distribution of interest here is also valuable, because you can either explain individual predictions in isolation and start getting things like saliency maps, or you can generalize it to other kinds of distributions of interest and recover things like integrated gradients and smooth gradients as special cases, but also be able to look at other interesting distributions of interest not covered by these methods. This method also enjoys a clean axiomatic treatment. I'm not going to go through all the axioms here, but a couple that I'll highlight is that it enjoys linear agreement, meaning that if the function behaves linearly over the distribution of interest, then you simply get the weight or the coefficient of the jth feature. It also offers distributional marginality. So this is a place where it differs from something like integrated gradients, in that we focus on requiring that if partial derivatives with respect to an input feature are identical for two networks, F1 and F2, not everywhere, but only over the distribution of interest, where the model was some part of the distribution in which the model was trained, for example, then the influences are going to be equal. So these are some places where there are some distinctive elements here that goes beyond what is available in the axiomatic treatment for integrated gradients. It generalizes existing methods. I touched on it briefly earlier. You can get integrated gradients and smooth gradients from this method as special cases. It also forms the basis of some more detailed pathway and pattern or graph level explanations. Here's an example of a paper that some of us wrote. It was published at ACL last year. It looks at internal explanations via influence paths. This is an NLP example. It's an LSTM model. Over here is a sentence. And the goal of this network is to predict what the number of the verb should be. Should it be an are or is? And in this example, what you can see is the actual subject, boys. The influence of this flows through this path and pushes the model towards predicting that the verb here should be the plural verb are, whereas this attractor noun is the confusing noun. It's pushing the model towards a prediction that the verb here should be an is. So you can get this kind of detailed view. And the model, this provides insights into classifications, understanding why the model is making errors. The model can also be compressed down these influential paths without changing the utility of the model, building some confidence that the explanation is actually a sufficient explanation. So some of the interesting results from that paper, and I encourage you to look at the paper for more details, is that the primary path from the subject alone provides strong signal for subject-verb agreement. Removing it actually breaks the model. And removing the primary path from the intervening noun in the previous example was this noun tree, which was pushing the model towards a confusing conclusion. Removing the primary path from the intervening noun is going to decrease the performance of the model if it is a helpful noun, meaning that, let's say, the subject was singular and the intervening noun is also singular, then removing the intervening path, the primary path from that intervening noun is going to decrease the performance of the model, because it was actually pushing it towards the right verb number as well. However, if the intervening noun is going to be confusing the model, like on the previous slide, then removing that primary path actually increases the performance of the model. So these are interesting insights into the inner workings of an LSTM, RNN, LSTM style models for NLP tasks that provide much deeper understanding into what's going on under the hood than you typically get from just looking at input feature importances or even looking at attention-like mechanisms for explanations. One quick final paper that I'd point you to is this recent paper that we put out on arXiv, which looks at influence graphs for BERT-like models. Now, BERT is quite a bit different from LSTM models. One is just the difference in scale. So as we go from influence spots, we need to really scale up our methods for identifying influential spots in order to be applicable to BERT. The second way in which it's different, and this is in some ways even more fundamental, is that BERT models tend to contextualize a sentence, parse it down into a structure, and this explanation for influence graphs actually surfaces that. So if you look at the example here on the right, this sentence, for this sentence, this is again subject-verb agreement. The model is trying to predict whether the verb should be singular or plural. The subject is pilots, and the green lines and the dotted green lines are where the influence is flowing to the prediction. And the other noun, the intervening noun here, the architect, is an attractor. Since it's singular, it's trying to push the model towards believing that the verb should be a singular verb. And you can see here that there's a lot of copy operations in this process that BERT does, and the exact nature of how the contextualization is done by the model gets surfaced through this form of influence graphs. Again, these graphs are quite sparse and quite interpretable, and therefore provides a rather clean understanding of how BERT is operating. With that, I'm going to quickly touch on the fact that while we focused on a few different methods for explanations spanning traditional machine learning models explained with quantitative input influence, which builds on Shapley values, as well as distributional influence and integrated gradient for explaining deep neural networks and pathway influences as well. There's a whole body of other work in this neighborhood that we have mapped out in terms of how they adhere to various axiomatic requirements. We won't have time to get into greater detail in the tutorial today, but very happy to take questions on it or have a follow-up conversation on this topic about the relative advantages and trade-offs that these different methods offer. This is a little bit more detail on how some other work in the neighborhood of the key pieces of work that we presented line up against various explanation framework requirements and axiomatic properties. Quantities of interest are missing explicitly from a number of these frameworks. The treatment for distributions of interest is also somewhat limited in flexibility. There's overlap, of course, in the use of gradient-based methods, but there are some important and substantive differences which matter in practice. Again, something that we would be very happy to get into more details of in follow-up conversations. With that, I'll leave you with a few takeaways. Good explanations answer a rich set of queries. They capture causal influence through gradients or intervention-based methods. They reflect the power of a feature, and we have touched on axiomatic foundations for that through the use of the kinds of axioms that are in Shapley values, but also Shapley and Almond-Shapley values, but also augmented with axioms for distributional faithfulness, which is extremely valuable, especially as you get into higher dimensional spaces. We'll touch more on robustness-related axioms in a later section of the tutorial. And then there is the question of accurate estimation of these explanations, where there have been significant algorithmic advances as well. And one of the nice things about these methods is that they provide a consistent and uniform foundation through the use of Shapley values, Allman-Shapley values, and variants in their neighborhood that apply consistently to statistical machine learning and neural networks across structured data as well as image and text data. And with that, I'll hand it over to Shaikh Sen, who has got his PhD from CMU and is currently co-founder and CTO of Truera, to do a demo of the TrueLens open source library, which covers a bunch of the material that I touched on in my section of the tutorial. Thank you very much.
Thanks for that introduction, Anupam. I'm Shaikh Sen, and in this next section, I'll share a brief demo of how to implement some of the key ideas discussed here. In particular, we'll demonstrate the use of TrueLens, a cross-framework implementation of distributional influence that is flexible enough to be used across different versions of TensorFlow, Keras, and PyTorch. To find out more, you can visit us on GitHub at github.com/trueerror/TrueLens, and also install us on pip. Let's recap some of the key concepts required for the distributional influence framework. So the influence itself is an average gradient over a distribution of interest. And in order to define it, you need this notion of a slice. The slice is some component of the network that you're interested in. It can be an internal layer, it can be the input layer, or it can be some temporal slice for recurrent neural networks. You also need this notion of a quantity of interest, which is a function of some part of the network, which could be the output of the model itself, the output of the model for a particular class, or it could be the output of a specific neuron in the model. You also need this notion of a distribution of interest, which is a distribution that inputs are drawn from that you would want the explanations to be faithful towards. So jumping into the library itself, let me briefly describe the different components of the library. Attributions is the component that does the actual work of computing the influence for a given model, slice, quantity of interest, and distributions. Model is a way to encapsulate the model written in different frameworks into a unified interface. The slices, quantity of interest, and distributions are the components we just discussed on the previous slide. And visualizations provide a set of useful tools to map explanations onto images. So in the rest of this demo, we're going to look at how you would use this library to explain a model for image classification. In this particular example, we are looking at a model trained in PyTorch, which is a VGG16 model trained on ImageNet. The first thing you would want to do in this particular case would be to set the backend, which is the library this model is built in, to PyTorch. In this example, we are downloading this model from Torch Vision and then encapsulating this model using a model wrapper to then make it like a TrueLens model. Once a model is a TrueLens model, for example, the model variable here, you can look at different aspects of the model, such as printing out its layer names and details and so on. In this example, we are going to be using this image of a beagle to see why the model classified it in a per particular way. To start off, we're going to uh, use a couple of well-known attribution methods, saliency maps and integrated gradients, to see how you would use the library to compute these. So the saliency maps method simply takes the gradient of the network's predicted class on a given input. The integrated gradients method addresses some of the issues with this by aggregating the gradient on a linear subspace of the model's input features. In this case, the input attribution method by default corresponds to the saliency map uh, method, and we also have a special implementation of the integrated gradient approach built into the attributions method. So computing attributions once you have a model is fairly straightforward, which is what we are doing here with a call to input attributions, which returns the input attributions, which is a vector and the same size of the image. And then we can use a mask visualizer to visualize what the attribution return. In this example, the model explanation actually returns parts of the image which are not particularly relevant to the classification itself. Now, when we run the same in input attributions, but with integrated gradients, we see that the model is actually focusing on important parts of the image for the classification of the beagle. Moving beyond these more basic examples, we can also use the library to discover important internal neurons. In this case, to define an internal neuron and its importance, we need to specify a specific slice. So the slice picks out a part of the network, which is the part of the network between the features 28 layer and the output of the model. And once we run this attribution, we find that the most important part of the features 28 layer is channel 328. In order to identify what this channel 328 is actually doing, we can now visualize this on an on the image itself by mapping mapping channel 328 back into the input layers, and we use the mask visualizer again to do that. In this example, we are now computing an internal influence from the input cut to the features 28 layer, and identifying the most important parts of the input layer for the features 28 layer at the top feature map channel, which recall was 328. Once we get back the most important parts of the image, we actually see a more focused explanation on the inputs, which identifies just the parts of the image that that channels was trying to capture, which includes the eyes of the beagle and the legs. Moving on to a slightly different example, we will now change the quantity of interest that we want the attributions to explain. So our example image contains both a bike and a dog, and while the top class was predicted by our model was a beagle, ImageNet also contains bike-related classes such as mountain bike, all-terrain bike, or off-roader. We will now use the quantity of interest, which is specific to a class, to view the attributions towards this specific class, which happens to be number 671. And once we do that, we find that the attributions actually pick up some parts of the bike as well, as opposed to just the dog, which we saw in the previous example. So this was an example of how you can um, modify the framework to flexibly try to explain different aspects of the behavior of the model. So that's it for the demo. If you'd like to find out more, please check us out on github.com/truera/truelens, and you can install the package
In this section of the tutorial, we're going to talk about how explainability and explanation techniques can shed light on various aspects of model quality. In particular, I'll begin by talking about privacy, and then hand things off to Anupam, who will discuss fairness. So it shouldn't come as too much of a surprise that when machine learning models are used in certain situations, they can potentially lead to privacy issues. So one example of this could be that the model makes use of certain types of protected information when it's making its predictions. An example of this would be an advertising model that uses health information to target ads. Recently, there's been quite a bit of news about the potential for using AI and machine learning in surveillance, and this has raised quite a stir about the privacy issues that could follow if this becomes widespread. And last but not least, the model itself could leak some private information in its training data, or potentially about the subjects that the model is applied to. And this last bullet is what we'll talk about in this section of the tutorial primarily. And I think that it's important to note that, especially when it comes to this last bullet, this sort of outcome tends to be unintentional. It's not an explicit goal of the person who trains and deploys a model to leak a bunch of information about the training data, but it does happen nonetheless if you don't take careful steps to prevent it. And when we find privacy violations like this, oftentimes it's symptomatic of some deeper model quality issues, right? So there's an interesting sort of potential for addressing not just the privacy issue, but also making a better model in the process. Okay, to talk about leaking information about training data through a model, we usually have in mind some hypothetical attacker. So we'll lay out a high-level threat model here to kind of guide our discussion of these attacks. So we assume that we have some sensitive training data that we create a model from. And of course, the attacker is given some kind of access to this model, and their goal is to interact with the model and potentially some background information that they have to make an inference about some parts of the private training data. And from the attacker's perspective, there are two modes of interaction that we'll talk about. The first is what we call the white box model, where the attacker has access to everything about the model, its training everything except for its training data. This includes the model parameters, obviously its architecture, and possibly some other details about how the model was trained, like its hyperparameters. The second is the black box model, where instead of giving the attacker access to everything, we just give them an Oracle interface so they can provide inputs to the model and see the model's outputs. And also we might assume in this case that the attacker knows which algorithm was used to train the model, in addition to hyperparameters. So the first example of an inference attack that I wanted to talk about is by Nicholas Carlini and his collaborators. And this was published in 2019. They were looking at language models, and what they found, to quote from the paper, is that users may find that the input, "my social security number is ... gets auto-completed to an obvious secret. Clearly, it would be problematic for many applications of language models if this were the case, if the models were basically just parroting specific details from the training data. And indeed, that is exactly what they found. So looking at a model that was trained on the Enron email data set, they found that by posing queries like this, in a systematic way, they were able to leak 3 pretty damaging secrets in under an hour. So they got 2 credit card numbers and 1 social security number. Now, from a model quality perspective, there's obviously an issue here because this signals that the model, beyond just potentially being overfit, actually memorized exact details from the training data. Seeing something like this would be an indication that not just is there a privacy issue, but also that the model might not generalize as well as one would hope. All right, another example of an inference attack is called model inversion. And this is work by myself with Tom Ristenpart and Somesh Shah back in 2015. We were looking at facial recognition models, like shown in the image here, that predict the identity of an individual who is shown in an image. And what we found is that it was possible to reconstruct sort of approximate examples that reasonably well resemble the training data. And by reasonably well, we did a mechanical Turk study and found that humans were, in the overwhelming majority of the time, able to match the reconstructed face from this attack to an image taken from the training data of the person who was targeted for reconstruction. Right. Now, the primary limitation with this attack is that the models we looked at were very simple. So the example on the left here was taken from a softmax regression model. We also looked at one hidden layer neural networks and denoising autoencoders to varying degrees of success. But subsequently, people have looked at more complex models, and the images on the bottom of the screen here are taken from some ongoing work of one of my students who's looking at much deeper models and has found that in some cases, not all the time, but there are some situations where it's possible to reconstruct pretty close approximations of specific training instances. So how does an attack like this work? Well, the algorithm that we published in the 2015 paper, shown on the left here, looks a little bit complicated, but really the idea is just to do gradient descent on the model input to try and maximize the neuron that corresponds to the class that you're targeting. The additional complexity just has to do with in-processing and regularization to try and enhance the image quality a bit more. But if the model is simple enough, then typically just doing plain old gradient descent works perfectly fine. This, of course, was a white box attack. We did try a black box variant with approximate gradients taken from finite differences. The results of that weren't as good, and the attack took quite a bit more time to complete. But more importantly, we found that if you are in a black box setting, say you're providing an API to a model, as long as you just quantize the output and release, maybe the most significant couple of digits of the confidence scores rather than full precision floats, then that's sufficient to prevent the attack that we had published. This actually relates to explainability because the key quantity used by this attack is the gradient with respect to the input. And this is, of course, exactly what something like a saliency map gives you. Right? So if you have a model that you can deploy with a black box API, but you also want to provide explanations along with the predictions, then you might be opening yourself up to an attack like this. So to give you an idea of what the original attack looked like on more complex models, these images are taken from a NeurIPS workshop paper by Meja et al. and they looked at VGG and ResNet models trained on CFAR. And here I believe they were targeting the bird class. As you can see, these reconstructions don't really look anything like your typical CFAR bird. But what they found is that adversarially trained models are significantly more prone to this attack. So the image on the bottom now is taken from an adversarially trained VGG model, and the result is pretty striking. It looks quite a bit more like a prototypical CFAR bird than anything that we had seen before. Right? I think that this is pretty interesting in light of the fact that others independently of this work by Meja et al. Have observed that robust models are also more explainable with gradient-based techniques. Klaus will talk about that in more detail later in the tutorial. But just to give you an idea, the three pictures on the bottom here are a car tire and two saliency map explanations taken from a regular model and an adversarially trained model. And clearly the adversarially trained model gives you a much clearer explanation. And I think the question here is, are robust models more prone to model inversion because they're robust, or does it really have to do with the fact that they're also more explainable, right? So if you, in other words, if you had a model that gave you similar explanations to what you get from these adversarially trained models, but wasn't necessarily robust, then would it also be more prone to model inversion? I think this is an interesting question. It seems reasonable to expect that they might, right? If the gradient is giving you quite a bit more fidelity about the source data, then you might expect that running gradient descent in a loop like we saw with the model inversion attack would give you a more faithful reconstruction. But more work needs to be done here to get to the bottom of this. Okay, so now we'll discuss a different kind of attack called membership inference. And this was originally demonstrated by Chokri et al. In a 2017 Oakland paper. The definition that we'll introduce in a minute here was some subsequent work by Sam Yom in CSF in 2018. But the idea with a membership inference attack is to basically determine whether a point that you're given was in the training data for a model, right? And so to formalize this, we'll assume that some data set is sampled from a distribution and a model is trained on that data set. Then nature will flip a coin, so choose a uniform random bit. And if that bit is 0, then draw a point from the training set. And if the bit is 1, then draw a point from the population distribution. Then the attacker is given the trained model, the point that was decided in step 3, and all the information about the population distribution that they need. And they win if they're able to determine the value of the bit, right? In other words, to determine whether Z came from the training data or not. So this might seem a little strange at first, right? Is this really a privacy risk that anyone cares about? Well, membership inference on its own is a privacy risk in some situations. If we think about, say, medical applications, where membership in the training data for a model could signal that an individual has a particular medical condition, then being able to determine whether somebody was in the training data would be damaging. But more importantly, I think membership inference has come to be seen as something of a general indicator for the leakiness of a model. How much does a model reveal about its training data? Well, sort of if you think of the lowest common denominator attack for anything that is going to try and infer facts about the training data, membership inferences is about as simple as it gets. So if a model is vulnerable to membership inference, then it certainly could be vulnerable to other kinds of attacks that infer more detailed information about specific training points. So one reasonable question to ask at this point is, why would something like membership inference even be possible? Because it really seems contrary to the whole idea of machine learning, where we want to get general trends about some distribution from many examples. And indeed, a result by Yom et al. In the same paper that the definition from the previous slide came from shows that overfitting, in particular a large gap in the loss in training versus test data, is sufficient for membership vulnerability, in that if you have that type of overfitting, then you can always find a membership adversary whose advantage, or the rate at which they win the membership inference game, is proportional to your generalization error. But somewhat surprisingly, overfitting isn't necessary for membership vulnerability. And in the same paper, they showed that if I have a stable learning rule, then I can always find a closely related learning rule that's almost as stable. But this sort of related rule, L prime, admits a membership adversary that can pretty much always predict whether a point was in that model's training data or not. Right? So I can generalize. Right? If I'm stable, then I generalize, but I can also leak perfect information about the contents of my training data to a black box attacker. So the next question is, how does that work? And the proof for this theorem sort of showed, existentially, that you can always construct such a model, but it might not be natural, right? We might not expect that models that generalize well and were trained using standard methods are going to leak a significant amount of information about their training data. But in recent work by Klaus Leno and myself that appeared in Usenix Security last year, we did find an example of exactly this, namely models that were trained using standard methods, stochastic gradient descent on benchmark data sets that generalized well, but nonetheless admitted an effective membership inference attack. To give you an idea of how this works, we were looking into how the way that models use their learned features could provide evidence of membership. So imagine a scenario where we want to predict whether an image contains a picture of celebrity A or celebrity B, and sort of in the source distribution, they're both wearing sunglasses about as often as each other, right? About 25% of the time. But if it happens that in the training set that we use to construct the model, celebrity A is more likely to be wearing sunglasses, and usually significantly more likely, right? Then, when we go to train a model from this data, we might expect the model to learn a feature that encodes sunglasses, right? And to also encode the fact that sunglasses are predictive of celebrity A, right? And we could actually measure the extent to which the model has encoded this by looking at the influence of the sunglasses feature on the outcome of predicting celebrity A, right? We would expect that influence to be greater for A than for B. Okay? And note that if we see this, we can use it as evidence of membership, right? If we're given a picture of celebrity A as a membership attacker, and in that picture, celebrity A is wearing sunglasses, there's a greater chance, right, that picture was from the training set than if we're given a picture of celebrity B and that is also wearing sunglasses. Right? And this doesn't have to do with how the model generalizes. It is possible for the model to learn to make general predictions, even if there's some degree of overfitting in the features that the model learns and the way the model uses those features. Okay. So just to kind of make this a bit more concrete and show you how this can happen on real data, many of you might be familiar with Labeled Faces in the Wild, which shows pictures of celebrities and many politicians in various poses on different backgrounds. When you train a model on LFW, the sorts of gradient-based explanations that you get tend to look like this. They focus most of their attributions on the center of the face, where the eyes, nose, and mouth, sort of defining characteristics that are useful for identification are. But in one example, we found that looking at an explanation of this training instance with Tony Blair on the distinctive pink background looks very different. The attributions aren't centered on the typical features that the model seems to use for prediction, but rather on the background, right? And that can be useful for predicting membership. So how do we actually do this? Well, we can use the internal influence measure that was described early in the tutorial to give us the information that we need to sort of construct a profile of how the model uses feature importance on training versus test data, right? So basically we can freeze the network up to a given layer if we want to characterize feature use at that layer, right? And then train proxy models on holdout data, which is distinct from the training data, right? So we can assume that the attacker has access to it, right? And then just measure the internal influence and estimate how useful a given feature is as evidence of membership in the training data, right? And from this, we can build an attack model, right, that takes influence measurements at attack time to predict membership. When it comes to defenses for threats like membership inference, the best way to prevent them is with differential privacy. To understand what differential privacy provides, it helps to sort of imagine a scenario where we have two independent worlds and we want to train a model in each of them. We're going to use almost exactly the same data, but we will allow it to differ in at most one row, right? And here we want to think of the rows as corresponding to the data for a single individual, right? And in either world, we'll also let the learning rule make sort of independent random choices when training the model. And what differential privacy would provide in a situation like this is a guarantee that the model that we're going to learn in either case shouldn't be too different, right, intuitively. More formally, what differential privacy says is that if I quantify over all of the sort of differences in the row that we're allowing to change, and all the possible outcomes, all the models that we might learn, right, then the probability of learning a particular model is going to be nearly the same, right? So the difference will be bounded by a factor of e to the epsilon, where epsilon here is called the privacy budget, is a parameter that we can tune to get a stronger or weaker guarantee as we need in a particular case, right? So smaller epsilons are going to give you a stronger privacy guarantee. Larger epsilons will give you a weaker one, right? So this is a really nice property for a model to have, especially when it comes to membership inference. But really, this bounds the relative advantage of any breach that we could think about sort of stemming from one person's data being included in our training data, right? Taking a step back and thinking about what this definition means from a higher level, because we're sort of quantifying universally over how the data can differ for a single individual. What we're really doing is kind of bounding the influence that one person's data can have on the model that we eventually train, right? And so by extension, if one person's data really can't contribute very much to the final model that we get, right, then we won't be able to learn very much about the data that any one person did provide when we look at the model, right? And this is a really close match when it comes to membership inference. Another theorem from the Yom et al. Paper says that if we have a differentially private learning rule, then any membership adversary will have a bounded advantage by a function of the privacy budget, right? So in particular, if our budget is less than natural log of 2, then we'll have a non-trivial guarantee about the best that any membership attacker could possibly do, right? And in practice, if we're actually going to use an implementation of differential privacy, like TensorFlow privacy, or any of the open source implementations that are available, then really the protection that we get in the model that we train with one of these methods is likely to be stronger than the sort of theoretical bound that we get from the mechanism itself, right? So when we prove that a learning rule is differentially private, nearly always we're proving an upper bound. We're proving that it's differentially private with respect to an epsilon that's an upper bound on the sort of effective epsilon that you'll get when you actually run that learning rule on some data, right? And this is evidenced by running membership inference attacks on models trained under differential privacy. So this figure is from the Usenix security paper mentioned in a previous slide, and we see that when we let the privacy budget range from a quarter all the way up to 16. 16, by the way, is a pretty astronomically large budget, considering that the bound scales exponentially in epsilon, right? In most cases, in every case except for on labeled faces in the wild, there really isn't that much of a change in the model inversion or the membership inference attacker's accuracy, which is shown on the y-axis of this graph. Now, there are some downsides that have to do with differential privacy that impact model quality. It's fairly well acknowledged that training accurate differentially private models is challenging. So this graph is taken from the Deep Learning with Differential Privacy paper by Abadi et al. That corresponds to the implementation in TensorFlow privacy. And here we're looking at the training and test accuracy of a CNN at 3 different levels of privacy budget. And in each of these models, the only part that was actually trained with differential privacy is the very top of the network. The feature extractors were pre-trained on independent data that was assumed to be public and therefore known to the attacker. And sort of even in that reasonably generous setting, you can see that the accuracy falls pretty far behind what the state of the art for CFAR 10 is. Okay, so to summarize our discussion on model quality, privacy, and explanations, we saw that model quality issues can lead to sort of unintended privacy harms. And that in some cases, these can be identified using explanation techniques. And the very fact that we can identify them using explanation techniques points to underlying model quality issues, right? this is a pretty new area, sort of looking at problems in the intersection of privacy and explainability. So there are lots of open questions and plenty of opportunities for good work, sort of building on some existing strong foundations.
We'll now dig into how explanations can help address questions of unfair bias. There has been a fair amount of attention paid to how bias might arise in machine learning applications. There was the well-known COMPAS study of potential racial bias in the way recidivism predictions were being generated by COMPAS. Here's another example of an image analysis task where, because there were a lot of images of women in kitchen making food, this particular image was being classified as being that of a woman. So gender bias in the way image in this task. Here's another example of in NLP tasks where this machine translation system, when translating from Turkish, which does not have an inherent notion of gender with certain kinds of pronouns, when translated into English, when the word doctor was associated with men and the occupation nurse was associated with women. So these are a few different kinds of examples of tasks, ML tasks, where bias based on race or gender makes its way into machine learning models. There's one aspect of it that we will dig into to begin with around the use of proxies in machine learning models. Consider a classification model. This could be a tree ensemble model, for example, or a linear model, or even some other kind of model. And let's say one question that we are trying to understand is, even if race was not explicitly supplied to this model, are there inside of these models proxies for race that were automatically learned through a combination of other features potentially? And is that proxy also important in making decisions that the model is making? In this paper that we wrote, a series of papers that we wrote a couple of years ago now, we examined this question in some detail and came up with some formal notions of proxy use. At a high level, there are two elements to this notion of proxy use. The first is a definition of what a proxy is in terms of a subcomputation or within the model, which is strongly associated with or is a strong predictor for the protected information type. So for example, inside of this model, there might be this subcomputation where through some combination of elements of zip code and income, the model might have inferred some derived feature which happens to also be strongly associated with or strongly predictive of race itself. And the second requirement is that this subcomputation, this proxy, also has a high influence on the model's predictions. And this high influence could be measured using, for example, some notion of internal feature importance, such as high QII or some other notion of feature importance as well. To make this notion a little more concrete, let's look at how proxy use might get instantiated in tree models and in linear models. This is an example of a tree which is branching on certain kinds of conditions. And if the applicant, let's say for this loan decision, came from a women's college and they're interested in this offer, and they're provided a certain offer, let's say for a high interest credit card. Whereas if the applicant is not from a women's college, then they don't. Then they are not given that offer, even if they're interested. Now, whether an applicant comes from a women's college or not happens to be a strong proxy for gender in this example. So at a high level, the way that proxy use in tree models works is that we take a tree model and we decompose it so that we have as P1, the proxy is the subtree of the model's AST. In this case, the women's college would be the example of the proxy. And then the rest of the model is the enclosing context. And the interesting thing here is when we find proxy use in this kind of model, it also includes a witness, a subtree over here that causes the use of that proxy. And this can function as an explanation for some discriminatory behaviors in the model. Specifically in this example, the proxy that the applicant comes from the women's college, which is a proxy for the gender of the woman, of the applicant, is the witness. And we can pinpoint that that's exactly the type of people who are being targeted with this high interest credit card offers. So having that kind of visibility really helps understand whether the use of this kind of proxy in this setting is justified or not. In a different example, it could have been that there was some forking here based on an individual's income. And if credit products are based on income level, certain kinds of uses of that information might well be justified, even if there happens to be a coincidental association with gender or race. But in this case, there's a rather direct use of that proxy in a way that would be very hard to justify. Once this kind of information is available, it can also be leveraged to mitigate the unfair bias by eliminating the dependence of the model's decision on unjustifiable proxies. And for a more detailed treatment of this problem, we encourage the folks to look at our paper in greater detail or come to us with questions during the Q&A session.
Okay, so I'll take over in discussing proxies for linear models. So here, of course, we're looking at models over n real-valued features, and the model is comprised of a set of real-valued coefficients. We're looking at the regression setting here. So the main thing that we have to decide when thinking about proxy use here is what are the decompositions that we're going to search over. So we could just pick individual terms or maybe subsets of terms. But it could be that some weighted combination of a subset of the terms actually gives a stronger proxy than any unweighted combination from the original model. So the set of components that we use here are given by a vector beta, taking values in 0 or 1, that basically just gives us a space of proxies corresponding to arbitrary weighted sums of any subset of the terms in the linear model. And there's a useful abstraction to use here when thinking about influence and association that we get when we view random variables as vectors in an inner product space with covariance as the inner product. So here, influence is the influence of a random variable on a model is going to be proportional to the magnitude of the vector, which it turns out is proportional to the variance of the random variable. And the association is measured by the angle between two variables. So you can see an example on the right of the slide here. If we have two random variables, alpha1 x1 and alpha2 x2, their association is given by the angle between them. And if we want to think about whether the middle vector is an influential proxy for alpha2 x2, right? Then we want to be looking at vectors that have a small angle with alpha2 x2, and those are given by the pink shaded regions. And if we want to look for vectors with high influence, then suppose we set a threshold that corresponds to the white circle, I would be looking for vectors that fall outside of that white circle. So that example middle vector, 0.7 alpha1 x1 plus alpha2 x2 would be an influential proxy for x2 in this example. And what this gives us for influence and association is basically that the influence is proportional to the variance of the component, and the association is proportional to the covariance of the component with the protected information type. Right? So Z is the protected information type, and we want to know whether Y is strongly associated with it. We just look at the covariance between Y and Z. And a really nice thing about looking for proxies in linear models is that it can actually be done fairly efficiently in a lot of cases. So the precise formulation of sound and complete proxy finding algorithm has us encoding the problem as a quadratic program where we maximize the influence of a candidate solution subject to an association threshold. But we can actually relax this into a linear program by taking a lower bound of the influence. And what this gives us is a problem whose solutions over-approximate those of the exact formulation as a QP. Right? So for the quadratic program, the quadratic program has a solution if and only if a proxy exists in the model. But for the linear relaxation, we might find a solution even if there is no proxy. But if we don't find a solution, then we know for certain that there is no proxy in the original model. And in most cases, the results of our experiments demonstrated that the linear relaxation is more than good enough to get useful results in practice. So now we'll move on to a different potential source of bias in machine learning models called bias amplification. And I'll start with an example given by Zhao et al. In an EMNLP paper a few years ago. And what they found was that in a semantic role labeling model, where in the training data, 66% of images labeled as having a cooking activity had female agents in them. In the models that they were able to train, that got reasonable accuracy, 84% of the agent roles in cooking images in the test data were labeled woman. Right? So we started out with a fair degree of bias in the training data, and the model amplified that, right, to introduce significantly more gender bias in the agent role labels, but only in cooking images. Right? So the first thing to realize about bias amplification is that in some cases it's unavoidable if we don't want to penalize accuracy, if we don't want to sacrifice the predictive accuracy of the model at all. In 2019 iClear paper. Sorry, there's a typo on the slide there. It should be 2019. We showed this with a simple sort of Gaussian naive Bayes data generative setting where we have binary response variable and Gaussian features that are independent conditional on the class. Right, and here the amount of bias amplification in the model is a straightforward function of the Mahalanobis distance between the means of the classes and the prior class prevalence. Right, so if the response label is very skewed and the features of the two classes are very close together, then the Bayes optimal model in this case is going to sort of learn a function that overemphasizes the prior class prevalence and kind of defaults to just predicting the most prevalent class. Right, and this gets extreme when the features are really close together, and it sort of smooths out as the classes get more distant. But this isn't the case in all instances of bias amplification. And if we think back to the cooking and gender labeling prediction task from earlier, right? One thing to sort of think about is that kitchen features are essentially sort of like weak proxies for gender in the data set, right? And if the model that we learn ends up giving these weak features too much influence in the predictions, right, then we might start to see more biased predictions if there are a lot of weak features with this sort of misassignment of influence, right? And so this is exactly what we find when we sort of control for weak features and their influence in the model. Is that the greater the number of weak features you have, and the more influence that you give them in the final prediction, the more bias amplification you have. But another really interesting sort of outcome that we found, at least when looking at linear models, was that this form of bias amplification seems to be especially prevalent in models that we train with stochastic gradient descent. So when we looked at linear binary classifiers that we trained with either LBFGS or SMO versus their corresponding variants with stochastic gradient descent, we saw essentially the same behavior with respect to bias amplification for both the logistic regression and the SVM model with SGD, and we saw a lot of variance in the amount of bias amplification with the other optimization methods. Right, so getting to the bottom of why this is, it seems that there's some inductive bias with stochastic gradient descent that sort of leads to this condition, but it's not totally well characterized yet. And getting to the bottom of that, I think, is important and interesting future work. But one more thing that we found was possible with this particular form of bias amplification is that a lot of it can actually be addressed with feature selection, right? And we can use explanation methods to help us identify which features we should prune from the model to reduce the amount of bias amplification. So the way that we do this is essentially to use some influence measure to measure the internal influence and identify weak features, right? And then formulate an optimization problem that tries to cut the weakest features while preserving accuracy. And what we find is that this works quite well in practice. So it's effective at reducing a lot of the bias amplification that you see sort of in vanilla training versus after this form of feature pruning. And in some cases, it actually increases the accuracy of the model, right? Because any prediction that we make sort of as a result of excess bias amplification is going to be an incorrect prediction, sort of by definition, right? And so when we remove that source of amplification, we actually get more correct predictions overall in the end. Okay. All right, so to summarize this brief section on fairness, fairness is a really complex problem with machine learning, and there really is no one-size-fits-all technical solution to the problem. But explanation methods can help, first in identifying instances of potential discrimination and helping us understand what the causes are, right? Especially when it comes to how a model uses protected information types, right? And in some cases, we find that explanation methods can give us information that we can use to mitigate some of the discrimination that we see in the model, and increase the overall model quality as well.
All right, so I'm Klaus, and I'm going to take you through the last module in this tutorial, which gives some insights about how to improve explainability by improving model quality. So one interesting finding about deep networks, which I'm sure many of you have seen before, is the existence of what are called adversarial examples. Basically, if we're given an instance, like say this panda here, we can add a carefully chosen perturbation, which is actually blown up here, in reality be imperceptible to a human, to change the model's prediction to an arbitrary class, so in this case, a given. And actually, in case you were wondering what a given is, it's a type of ape, and maybe this black one here could reasonably look like a panda, which actually makes this canonical example from the literature maybe not so great, since the fact that a panda could maybe be reasonably mistaken for a given turns out to not really have anything to do with why this is possible. But basically, it turns out that this type of attack is really easy to do on neural networks that are trained in the standard way, and you can pretty much cause arbitrary classification mistakes if you choose your perturbation carefully. So just to recap, we can attack the prediction of a model by selecting what we call an adversarial input. So basically, we have a model that takes an instance and makes some prediction. So say on this clean or benign input, our model might predict llama, which I guess is correct here. But we could give it an adversarial input that we manipulated to make the model predict, in this case, cat on a perceptually identical image. And anyway, it turns out that explanations can be manipulated in an analogous way. So basically on this clean input, we have a model that again predicts llama. And if we compute an explanation on this input, then we can see that the sort of areas with the highest attribution are highlighted in red, and it seems mostly concentrated on where the llamas are in the image, which is what we might hope for. But then we can manipulate the original image with some small imperceptible change where the model still correctly predicts llama. But if we compute the attributions, we get this, where we can see that the attribution map changes significantly. Pretty much all the attribution moves to the right side of the image here, where it seems there was really nothing interesting going on in the image. So this should maybe be a bit concerning because on a point that's super similar, the explanation we get is totally uninsightful. And it's actually maybe even just concerning that in such, for such similar points, you could have such different explanations. So this really raises the question, which is if explanations can be so easily manipulated, can we really trust them? And basically, is there something wrong with the explanation method that gives rise to these kinds of anomalies? Or is it something else? And basically, the idea is that, or the sort of question is, can we really expect interpretability using these methods that we've covered so far when we have these kinds of inconsistencies? And to give some foresight, the sort of thesis in this section, or this module, is that the root problem here is with the model and not really the explanation. To get an idea of why this may be, let's consider an example. So say on this image, by changing just one pixel in the region that's circled there, where really nothing's going on that's relevant to the class panda, let's say that we can change something there and prevent the model from predicting panda. So for example, we might get this image where we just change one pixel and the model predicts some class besides panda, so maybe given or maybe something else. And then suppose that we get this explanation on the original image where the only salient pixel is the sort of blue pixel that we change to red to prevent the classifier from predicting panda. And I guess this explanation seems weird since it shouldn't have anything to do with why this image is a panda. But basically, is it really wrong to say this pixel was important? Because we can see that if this pixel had actually taken a different value, we actually could have ended up with a different prediction. It could be that even locally, this is the most direct way to change the class. And so the pixel could in some ways be reasonably considered the most important pixel for why this was a panda and not something else. And at the very least, this pixel really should be considered causally relevant to the prediction with respect to how the model actually works, because we saw that an intervention here could change the outcome. So essentially, while the explanation here maybe seems strange, it really comes down to the model's strange behavior. So basically, the fact that you can get an arbitrary explanation maybe suggests simply that a model is capable of arbitrary behavior in the first place. So just to reiterate, the key idea in this section is that what may seem like bugs in the explanations should really be seen as evidence for model quality issues. But one sort of point here is that we should really insist on faithful explanations in particular. In other words, we want our explanations to actually reflect what the model is doing rather than like wishfully whitewashing strange aspects that might be a flaw in the model's behavior to sort of hide them. But assuming that our explanations are faithful, then strangeness in the explanation is really just an indication of something strange the model is doing. And we may sort of hope that our models can be explainable or interpretable, and this could definitely be an achievable goal. But for example, the existence of adversarial examples in standard models shows that it's easy for a model to have strange flaws that suggest they're not at the point where they're seeing the same things humans would see. So it's maybe not that strange to expect that for a model to make comprehensible decisions, it shouldn't have behaviors that make absolutely no sense to people. And just to hammer home this idea of faithfulness a little bit more, let's briefly revisit attacks on explanations that we had covered a couple slides ago. And before we looked at instance-based attacks, where an instance can be adversarially manipulated to give modified explanations. But here we're going to look at a model-based attack. And in this type of attack, we change a model to make similar predictions to a standard model, but produce much different explanations. So in the standard setting, we have some data and we train a model to make good predictions with some loss function. But in a model-based attack, we can actually use this standard model to construct an adversarial loss function, which we use to train another model to make the same predictions as the original model, but with different input gradients on the same points. So basically what we get is, like on this instance here, the original model predicts 2, and the explanation looks like this. I guess maybe not super insightful, but that's what it is. But if we pass in the same instance to our adversarial model, we still predict 2, but the explanation is now the answer to everything, which is 42. So even though these models make the same predictions on the training set, their explanations are fairly different. And there could be a few interpretations of what this means, but our view here is that this difference in gradients between the models is actually significant, and it's really should be considered correct for the models to have different explanations. Basically, even though the model's behaviors may be the same on some specific distribution, doesn't mean that they'll be the same on all inputs. So in fact, if the functions were actually identical, their gradients would be identical too. So we kind of know that if the gradients are different, that these aren't exactly the same function. And we've seen from the existence of adversarial examples that sort of in distribution points aren't really the only points that we should care about for a good model. So we want to be able to distinguish between models that make different predictions on points, even on points that aren't directly on the data manifold. And as we can see from this example, these two models have the same test error, but they're still not guaranteed to have similar behaviors in a sense. So we really shouldn't consider them to have the same quality. But all right, so now what? We've established that what appeared to be bugs in faithful explanations are actually evidence of issues with model quality. And ideally then on well-behaved models or sort of quality models, we shouldn't see such strange behavior in the explanations. In other words, we should be able to get better explanations if our models are better. I guess quality explanations require quality models. So then how do we improve the quality of our models? And to get towards one possible answer to this question, we're going to take a look at the concept of local robustness. So just as a definition here, we say that a model is locally robust at a point X if all points within a distance of epsilon of X are given the same label as X. So geometrically, we can think of this as requiring that there are no decision boundaries that intersect the epsilon ball centered at X. So in other words, near certain points of interest, we can preclude the model changing its prediction as a result of small perturbations. So the adversarial example from earlier, you may have sort of realized is an example of violation of local robustness. So if we have a benign input, like this one here, this panda, we can look at the neighborhood around the point and see that it intersects the decision boundary. And that means that we can find an adversarial example like this one here. So local robustness is a useful property for a model to have on the points that we care about, but how do we actually get a model to have this property? The standard approach to training basically just takes some training points like these and finds a boundary that separates them by label. But this pretty much gives us no guarantee at all that we won't have decision boundaries near points that we care about. And actually in practice, we pretty much always end up with adversarial examples. So here we can see that that's the case with this boundary that was come up with here. But sort of one intuitive approach to get local robustness is to use what's called adversarial training. And basically, we can think of this as replacing the original training points with the sort of worst case adversarial examples and training with those. And of course, an adversarial example is defined with respect to an existing boundary. So we don't just use a static data set of adversarial examples. That wouldn't work. But instead, we sort of recompute them as the decision boundary changes. We hope to converge to a model without adversarial examples like we sort of have here. And just to sort of quickly note, there are also other ways of training robust models. Some are also based on this general intuition, and some do other things like trying to put other constraints during training or even post-processing that would help us rule out the possibility of adversarial examples. But anyway, what's particularly interesting about robust models from an explanation point of view is that recent work has found that robust models are more interpretable. So for example, it's been found that the input gradients on robust models tend to look better in the sense that they line up better with the salient objects. So here we can see in the first row, there's some images from various standard data sets. And in the next row, we have what the input gradients look like on a standard model. On some of them, arguably, there's a bit of action around the areas we might expect, but for the most part, they're pretty non-insightful. On the other hand, in the next two rows, we have the explanations on two different robust models. And so basically, our definition of robustness from before, we can define what we mean by an epsilon ball differently by changing the norm. And so the L2 norm is probably the most intuitive since it corresponds to Euclidean geometry, which everyone's used to, but it's also common to use the L infinity norm. So that's shown in the third row here. And we can see, maybe especially on this MNIST sort of model on the left, here that the gradients on the robust models look a lot better aligned with what we'd hope they would, which maybe shows these robust models have a better characterization of what's important to each class. And similarly, the feature visualizations on robust models look better and more intuitive. So I guess just to be clear, the feature, or I guess I maybe should say class visualization, is obtained by optimizing to maximize the model's prediction on a particular class, given some starting point, which is shown as the seed in the figure in this. And it sort of lets you isolate what a network is particularly looking for a specific neuron or class. And so we can see here on the bottom, we have some feature visualizations for a standard model. And like, you know, the top row there is the visualization starting with a picture of a dog there, and the other one sort of starting from some kind of noisy gray background. We can see that, like, really these aren't recognizable at all. You wouldn't be able to pick out what class any of these correspond to, and they kind of all look the same. But on the other hand, you know, if we look, you know, at the corresponding column for the robust model, we can see maybe this first feature here is, you know, like trying to optimize the frog class because it looks like we see some frogs there. The next one's maybe sea turtles, but at any rate, like we can sort of really see what's going on there, and that kind of shows that the model came up with a better sort of hypothesis for sort of canonical examples of these classes. So this looks a lot better on robust models. But yeah, so that's cool. Like robust models seem to be more interpretable, which maybe suggests robustness should be in your toolbox for if you're trying to build explainable models. But the last thing I want to talk through here is just a bit of sort of interesting intuition as to why robust models are more explainable, which comes from some recent work. So the hypothesis is, and this is from Ilias et al., that standard trained models use what we'll call non-robust features to make predictions. And we'll cover in just a bit what we mean by non-robust features in a slightly more formal sense, but just to get a sense, here we have an image of a frog, and on the right is an example of a set of non-robust features that a model could use to predict that this is a frog. And so we can see that these non-robust features don't look super meaningful, but they turn out to still be valuable and reliable predictors on the data distribution. So it may be fair to think of them as these sort of super high frequency features that are potentially useful, but not really perceptible to humans. And now we'll just, give a quick, slightly more formal characterization of what we actually mean here by non-robust features. So first, by a feature, what's maybe useful to think of is a neuron in a neural network. So more generally, it's really just a function from the input, like an image, to a real number that represents that feature's value. So this could be some linear combination of neurons, actually, or even just sort of potentially realizable neurons as well. But it may be conceptually simpler to just think of them as neurons in a network. And then we say the feature is non-robust on some data if the feature value correlates with the labels of the corresponding instances in that data set, but the correlation gets broken under small perturbations to the inputs. And then to get a sense, on the other hand, of what an actually robust feature looks like, we can use a sort of neat trick from this same paper to generate a robust feature set. So first, we use the observation that even though we said that non-robust features can be useful for classification, in the setting where we're training a robust model, non-robust features are actually no longer useful since robust models have to still work under small perturbations and non-robust features don't. So that means that a robust model has really no reason to learn non-robust features. So in other words, robust models should only learn robust features. So what we can do is we start with some instance, x prime, and randomly initialize it. And then we optimize it, where our goal is to match the features a robust model uses on a particular training point, like say this frog here. So basically our optimization goal is to make it so a feature extractor from a robust model, which we can think of as just the output of the penultimate layer of a robust network. And we want the representation to match for both the original point and x prime. And since random noise won't contain any features correlated with frogs, so where we started doesn't have any sort of non-robust or robust features, we sort of expect that this optimization process is going to only add robust features to x prime, since anything else won't be relevant to matching the feature representation of the robust model. Anyway, we can see that this sort of robustified image is still fairly recognizable as a frog. So now, putting all these things together, we have the following hypothesis. So first, standard models make use of non-robust features, which are non-interpretable features that are nonetheless predictive. For example, something like this. And we might also occasionally get robust features like the one on the right, but we're still going to use a lot of these non-robust features. And in fact, the model might have a preference for them. And on the other hand, when we get a robust model, we don't expect it to use any of these non-robust features. So it'll only use robust features. But non-robust features are inherently not interpretable compared to the robust features, which make more sense to humans. So the explanations in robust models won't contain sort of references to the non-robust features, which appear strange to humans, and that leads to more interpretable results. And anyway, that's it for a bit of a deep dive on improving model quality for better explainability, particularly looking at robustness. But just to summarize, we pointed out that what appear as bugs in faithful explanations are actually evidence of model quality issues and not necessarily a problem with the explanation itself, since faithful explanations just describe what the model is actually doing. So in order to get good explanations, we need quality models. And finally, robustness may be one way to achieve better model quality and interpretability. There could be others, but that's sort of one thing that should be in your toolbox if you're looking at trying to get explainable models. And I guess I'll be happy to take any of your questions now. So thanks.